Let's talk about the product rule a little more and do it through a few examples and applications. So let's just start with what is our product rule. So our product rule, and I'll project the full definition too, but let's just write it out here so we have it to work with as we work these examples. So what the product rule is referring to is if we want to take the derivative of two functions that are in a product that are multiplied together. So if we want to take the derivative of f of x times g of x, what we do, and we proved it in the previous video, is we take the derivative of f, multiply by g, plus the derivative of g, and multiply by f. And in short notation, if we wanted to just, write this at the top of our page, because that can sometimes help to remember these rules, is to rewrite them multiple times, we could write f prime times g plus g prime times f. Now I just wrote it out in the prime notations. We could have brought the derivative operator throughout as well, but I'm going to leave it like this. So this is kind of our little reference. We can jump back to this as we're going through these examples to remind us of the product rule. Okay, let me go ahead. I will project the official rule here for just a second too, in case you need to screenshot it. All right, so here it is, highlighted the shorthand notation that I wrote on the other screen. And just again, as a reminder, I mentioned this when I proved the product rule in the previous video, but I do order it just slightly different than our textbook orders it. It's the same thing, I'm just using the properties of multiplication to rewrite multiplication and addition to rewrite it in just a slightly different organization. I do that because it corresponds a little more directly with the quotient rule, which we're going to do next. All right, so let's get in here and let's do some examples. So if I have this particular function, y equals the square root of x times the polynomial 2x squared minus 7x plus 4, I see that this is a product. So using the product rule is one of the options that I have. And so that's what I'm going to go ahead and do. Now, in this notation here, this would be my f, my first function, and this would be my g. Now, simply because I'm taking derivatives, I'm going to go ahead and write that square root of x is x to the 1/2, just to get myself set up a little bit better. This is that rewriting step that we've practiced quite a bit. So we're going to do I'm not taking a derivative yet. That is simply a rewrite on that exponent on that root. So just to rewrite it, instead of square root of x, write it as x to the 1/2. Now I'm going to go ahead and I'm going to get in here and I'm going to take the derivative. So in order to do that, I'm going to write out all the steps here. dy dx, I'll use Leibniz notation since we were given it in y. dy dx, I'm going to have to take the derivative of x to the 1/2, that's my f prime, and then I'm going to multiply by 2x squared minus 7x plus 4. That's my g. So here is in the notation from the shorthand notation that we wrote to remind us over here. Here is my f, that will become my f prime times g, and now I need to add, and I'm noticing I'm going to run into my actual product rule right there, so let's scooch that off to the side a little bit so I have some space and finish this out. Then I'm going to take the derivative of g. So that's going to be 2x squared minus 7x plus 4 times, now that, remember, is going to turn into my g prime, times f. Now f is just x to the 1/2. I'll put it in parentheses, even though it is just a single term there. So what I have here, this is going to become my g prime times, and this is my f. Okay, and there we've got our product rule. So let's go ahead and actually take those derivatives now. So that was just the setup, and I will do a few of those as we get used to this rule, where I'll write out that setup so we can see what we're taking the derivative of, and then we'll just start getting in there and getting our hands dirty with derivatives and doing these. So this is going to be 1/2. As I take the derivative, I'll apply that power rule. 1/2 x to the minus 1/2 times 2x squared minus 7x plus 4 plus, and then when I take the derivative of this polynomial right here, it's going to be, I'm going to apply power rule, excuse me, power rule to each of those terms. So I get myself 4x minus 7, the constant of course is 0, times x to the 1/2. Let's go ahead and put this in parentheses too. Okay, so again, what I have right here, I'm just going to write it and then erase it. This is f prime times g plus g prime times f. That is the definition of the product rule. So, and we proved it. We not only is it the definition, we actually proved that that was what the derivative of a product was. So now I have the derivative. This is dy dx, but it's just kind of in a messy form. It's in a form that we don't particularly like. I'm not going to accept an answer like this. This would get you part of the credit because you've taken the derivative, but you haven't simplified it at all. So we want to make sure that we get in here and we clean this up as best as we can so it becomes a usable form of the derivative, something we can look for horizontal tangent lines with, or whatever other data we might want to get from the derivative. So I'm going to get in here and I'm going to say, what could I do here to simplify? There's several ways we could go about this. We could distribute, collect like terms, all of that. But before I do any of that, I'm just looking at those fractional exponents and I'm thinking to myself, I kind of want to just pull those fractional exponents out so I don't have to deal with distributing them. So I could pull out an x to the minus 1/2. So if I pull out, let's pull out a common factor equal to, you know what, I don't even like that 1/2. I'm even going to pull out the 1/2. I'm going to pull out a common factor of 1/2 x to the minus 1/2. I mean, if we're going to simplify, let's get it really nice and simplified. So let's pull out 1/2 x to the minus 1/2. So I'm going to pull that from each of these terms. I'll write the steps so that you can see it. Hopefully you can just follow along. Normally I wouldn't write this step in, but you know, I'm pulling that factor from each of those terms here, and that's going to give me, so my derivative now is going to become simplified into 1/2. I'm going to have that x to the minus 1/2 out here. And let's see what would be left behind. Clearly this whole, this whole factor, that's going to cancel. So what's all that's left from that first term there is the 2x squared minus 7x plus 4. Plus, of course, we've got the 4x minus 7. Now, when I divide right here, what we do is we just apply our rules of exponents, and we're dividing by 1/2, so that's actually multiplying by 2. So I get 2x to the 1/2 minus a minus 1/2, so that becomes just x to the first power. And look at how nice that interior of my brackets here has become. I no longer have fractional exponents. I have something, two polynomials. I can easily expand the second, the binomial times the monomial there. I can expand that and combine those into nice, clean derivative here. And that's our whole goal. So while the derivative itself we did up above, now we're getting into all that simplification. So let's just see. What does this become here? This is, when I distribute that 2x, I get 8x squared minus 14x, and then I'm adding, I could drop the parentheses on that first term and I could add the 2x squared and the 8x squared and get myself 10x squared minus 7x minus 14 minus 21x, and then we still have the 4. And we've got this 1/2 x to the minus 1/2, but that's the same as 2x to the 1/2 in the bottom, and this is dy dx. All right, now this is a nice cleaned up, I'm even going to drop, I don't even need those brackets anymore. I'm going to drop those brackets. This is a nice cleaned up derivative, one that's very user friendly, let's say, one that I can use to do all sorts of things. So 10x squared minus 21x plus 4 over 2 square root of x, if we prefer the root version. If we prefer to write a square root instead of a rational exponent. And there we go. And now we can do all kinds of things. Like if I wanted to know where this has a horizontal tangent, I could set it equal to 0 and look at where that polynomial in the numerator equals 0. Remember, if polynomials don't factor, we still have techniques for calculating roots. We just use quadratic formula or the square root property. Okay. So that is our derivative. I want to mention, and I think what I'm going to do is I'm going to speed up the video here and show you that there was actually another way to do this one. And some of you might have seen at the beginning, like, why is she doing it this way? Why is she going through product rule when this could have been rewritten from the beginning? So let's just add that into this video so we can see that. So notice that this particular function, y equals the square root of x times 2x squared minus 7x plus 4, could have been expanded first, and then we actually wouldn't have even had to use the product rule. So I'm going to do that just so you can watch that. I'll speed it up since it's a little bit of a review from the last time, but let's go ahead and just show that and show that we do get the same answer, even if we didn't use product rule, if we did some algebra first. So check it out. There are our two different ways to have computed that derivative. We could either just apply the product rule to it, or if we had noticed there was some algebra to be done first, we could have worked through the algebra and then taken the derivative without the product rule. So two options on this one. Sometimes, though, we don't have two options. So let's take a look at one where we are going to apply the product rule in some context. Okay, so here we clearly have a product, and it is of two different functions that cannot actually be combined or brought together like our previous one where we had two options. So we've got the square root of x times e to the x. And on this one, let's go ahead and find f prime of x and f double prime of x. Let's find both the first and the second derivative here. So to do that, again, we're going to remember, and I'll just write it maybe up here at the top, that f times g, if we want to take that derivative, so we're taking the derivative of f times g, actually let's use prime notation. So if we're taking just our product rule, if we're taking the derivative of f times g, we're going to get f prime times g plus g prime times f. So we'll keep that in mind and we'll do repeated derivatives here. So I'm going to zoom in here. We have a second part to this once we've got the derivative, and we'll come back and we'll talk about the tangent and the normal line. So let's take f prime of x, thinking this is our f and this is our g. And so again, I'm going to write it out. I'm going to take the derivative. You know what I want to do? I want to write that as x to the 1/2 times e to the x. Much easier to work with that fractional exponent. So we can apply our power rule. Times e to the x plus the derivative of g, which is e to the x, times f, x to the 1/2. Let's put those in parentheses just to really designate one more time. So here's our f prime times g plus g prime times f. And again, I'm gonna for these first few examples write out all these steps with the derivative operator here, so we're very clear about what's happening, and then we'll get into simplifying our steps a little bit and just jumping right to the derivative. So x to the 1/2 when we take the derivative becomes 1/2 x to the minus 1/2 times e to the x, plus the derivative of e to the x is simply e to the x times x to the 1/2. Okay? Now, I could leave it like this and simplify here, but I'm going to do what we did on the last one, and I'm going to say, you know what, I want to clean this up. I mean, I already know I'm going to have to take a second derivative. I have to take the derivative of this function. So if I could get it in its most cleaned up form, that's what I want to do. So I'm looking here and I'm saying, you know what? What's the common factor here from each of these terms that I could pull out? And I see an e to the x. And you know what? I'm going to do the same thing that we talked about on that last example. I see that fraction. I'm going to pull out a 1/2. And I'm going to pull out an x to the minus 1/2. So I'm going to pull that. You know, essentially this is what I'm doing. Dividing each of these terms. Sometimes it helps to have this visual as I put that common factor out in front. Okay, so I'm going to move that common factor to the front. So I'm going to end up having 1/2 e to the x, x to the minus 1/2, and see what I get left behind. Notice in this first term, all that is left here is a 1, the constant 1. Okay? And then in the second term, the e to the x cancels. I do have a 2 because I'm dividing, you know, there's a 1 right here, and I'm dividing 1 by 1/2, so I get 2. E to the x is gone, and x to the first power, because 1/2 minus a negative 1/2. So sometimes it helps to, I put that there in red, sometimes that helps just to see what's happening as I'm pulling out that common factor. So this is what f prime of x is equal to. We could simplify that just even a little more, I think. Drop that negative exponent, so we've got e to the x times 1 plus 2x divided by, now in the denominator, we're going to have 2x to the 1/2. Or if we really like it better, we could write this as f prime of x equals e to the x 1 plus 2x over 2 times the square root of x. And I think that version might be nice when we go and find equations of tangent lines. So I will leave it in that form. Okay, so there's my first derivative. Now to take the second derivative, because we haven't done the quotient rule quite yet, and this f prime of x, the way I've written it here with the root in the denominator, does involve a quotient. So in order to take the second derivative, I'm going to work with this version, where we've already written it as x to the minus 1/2. So I'm going to work with, these are equivalent, so I'm going to work with this version. And let's take the second derivative. So f double prime of x, now we're taking the derivative of a derivative. So we're really looking back here and we're saying we need to take the derivative of this function. Notice in this function that we actually have the product of 3 different functions, like an f, a g, and an h. Okay, I'm going to actually rewrite that down here so I have it in my space. So I've got 1/2 e to the x, that's like my f, x to the minus 1/2, and 1 plus 2x. So we actually have to think about this repeatedly. We have to think that this is like an f times, let's call this g to start off, but then when we take the derivative of g, we're going to have to think of this like 2 functions in and of itself. We could call that like f1 and let's call it f2 and g2. Okay, so as we write this out, you're going to watch me do this. There's some layering here. So as we take this derivative, f double prime now, we are going to take the derivative of the first function, which is 1/2 e to the x, times the second function, x to the minus 1/2 times 1 plus 2x. Plus, then we're going to take the derivative of x to the minus 1/2 times 1 plus 2x, times 1/2 e to the x. Okay, so I want to talk about this. So here we're going to take the derivative of e to the x. So the derivative of e to the x is just e to the x. The derivative of the natural exponential is itself. So this is just 1/2 e to the x times x to the minus 1/2 times 1 plus 2x. Now, I have some choices. This is a product. This is an f times g right here. Okay. Now, we could reapply the product rule. Okay. We could think of this, do this all the way out. This is f prime times g plus g prime times f. That's what we did when we looked at one like this in our previous example on this video. But I'm going to say right now that before I take this derivative, I don't actually want to apply the product rule a second time here. So before I apply this derivative, I'm actually going to do the distribution. So that said, if you wanted to do the product rule, you could, and you'd get the same thing. That's what I just showed in that previous example. But I don't want to do it that way. I want to get in here and I want to just say, you know what? This right here is the same as taking the derivative of x to the minus 1/2 plus 2x to the 1/2. And that I don't have to apply the product rule to because that's not a product. And that's what I want to do. So I'm going to take that derivative. The derivative of that is going to be minus 1/2 x to the minus 3/2 as I apply the power rule, plus 2 times 1/2, so that's just 1, x to the minus 1/2 times 1/2 e to the x. And now I have the derivative without having to layer the product rule here. Now, again, we could have, that wouldn't have been the end of the world. And so now we just want to simplify this. So let's go ahead and get in here. Let's simplify this, maybe even speed it up, but we're going to distribute, pull out some common factors, do some things like that, because this is kind of an icky derivative here. So, the first thing I'm thinking is, why don't we pull a -1/2 x to the -3/2 out of here? So that's going to leave me with a 1 minus 2x, and then I've got my 1/2 x e to the x. I need to zoom in. Carry this guy down, 1/2 e to the x, x to the minus 1/2, 1 plus 2x. Okay, looking at this and seeing what can we simplify here. Let's continue here. I just caught that I had carried an extra x down from the line above. I had 1/2 e to the x. This should also be 1/2 e to the x. So before we go any further in the simplification in this video, I have that highlighted so that I can erase that and fix that. And that should be actually just 1/2 e to the x. Now, this is all kinds of messy in my eye. So I am going to do a little simplification here on that second term, and then we'll look for a common factor. Definitely feel like I can see some e to the x's and x to some powers that I'm going to want to pull out. So I'm thinking that we'll do that right after we get this simplified. The second term here, I see a -1/2 and a +1/2. Let's make that -1/4. Pull the e to the x to the front, x to the -3/2, and 1 minus 2x right there. Okay, now I want to pull out a common factor here. I look at these two and I think, you know what, algebraically, we can definitely make that better. So I am going to pull out a common factor here of 1/4. Let's get rid of that fraction, or pull that fraction, not get rid of it, but pull that fraction out. 1/4 e to the x, and let's take x to the -3/2. Let's pull all that to the front. That'll be my common factor. And so let's put this common factor in the front. We've got 1/4 e to the x, x to the -3/2. And let's see what we are left behind with. So we're going to end up with a 2x times 1 plus 2x here. Here we're going to end up with a -1 times 1 minus 2x. And so that's what we have left behind after pulling out that common factor. And then we just continue down to simplify just a little bit more. 1/4 e to the x, x to the -3/2. Let's go ahead and distribute this out and see what we get. We get 2x plus 4x squared minus 1 and plus 2x. And so what that's going to leave me with inside that expression is 4x squared plus 4x minus 1. And that is our second derivative. We could, of course, we've got that negative exponent, and I do like to drop my negative exponent, so we would be left with a e to the x in the numerator. Let me write this a little better. E to the x and a 4x squared plus 4x minus 1 in the numerator, and a 4 in the denominator, and an x to the 3/2. And if we really wanted to, let's write the equivalent form with the root. 4x squared plus 4x minus 1 over 4 times the square root of x cubed. And either of those forms is fine, but we do want to leave our expressions, our functions, with positive exponents. We don't want to have negative exponents in our answers. Now, whether we leave the rational exponents or not, that is up to you, and that would be fine if you want to leave the rational exponents. And so here we go. So there's our second derivative. So this was the second derivative of that original function, taking the first derivative and taking a second derivative with it. But now we're actually going to go back to that first derivative and do an application. be taking the derivative. But now let's do something with it. Let's find the equation of the tangent line and the normal line. So let me take just a quick little sidebar here for this piece. The normal line, let's do a side note here. Let's define the normal line to a curve. So when we say normal line, what does that mean? And that is going to show up just, periodically we see that. And it's a nice application, extension beyond just the tangent line to talk about the normal line. So given a curve, y equals f of x, at a point, the normal line at a point, at x f of x, is the line that is perpendicular to the tangent line to the curve. Y equals f of x at the point x, f of x. So what does that mean, right? Like that's a lot of words. What that means, let's just do a quick little graph. Like if we have a curve, and we know how to find tangent lines, we've been doing it for, feels like, been doing it all semester basically. If we have the tangent line, let's do this actually with a ruler so we can make it really nice. If we have a tangent line at some point, let's just make it at this point right here. So if this is our tangent line right in here, so at this point, let's be real specific here and call that A. So at this point A, f of A, I'm going to actually do that in black. So at this point A, f of A, this red line is what we call the tangent line, the point that just touches the curve and represents the behavior of the curve at that instantaneous point, in time almost, right? If we were to zoom in and look at that instantaneous rate of change of that curve right at that point, A, f of A, that's what is the tangent line. And it has, by the way, let's keep this going just as a review. The slope of the tangent line, remember, is the derivative at A, the derivative of the function at A. So the derivative at A, we know what the slope of the tangent line is. And the nice thing about normal lines are perpendicular. And so if we were to get in here and do the perpendicular line, it's not going to be perpendicular. I should have looked at the angle of the tangent line, but this will eyeball it. This will be close enough. This line right here, where this is a 90-degree angle, is the normal line. And the normal line, the slope of the normal line, is perpendicular to the tangent. So it is -1/, it's the negative reciprocal of the slope of the tangent line, or -1/f prime of A if we want to get very specific. Okay, so that's the piece that if we hear the word write the equation of the normal line, we want to just remember that it is perpendicular. The normal line is perpendicular to the tangent line. So the normal line is perpendicular to the tangent line. So if we knew the slope of the tangent line was 5, well then the slope of the normal line would be -1/5. All right, so that said, let's actually do both over here. Let's find the equation of the tangent line and the normal line to this curve at x equals 1. So we need the curve and we need the derivative to do this. So let's write, just so I can zoom in and have a little space, let's write the function. We already were given the function square root of x, e to the x, and we already found the derivative, so I'm not going to go through that work again. The derivative was e to the x times 1 plus 2x over 2 times the square root of x. Okay, so let's use those. use those two functions, the function and its derivative, to write the equation of the tangent line at x equals 1. So first of all, at x equals 1, we need to know what the point is. So what is the ordered pair? So at 1, if I plug 1 into the function, f of 1, what I find is, of course, that's going to be the square root of 1 times e to the first. So 1e, or e to the first power. So we know we're going to be passing through, so we've got the point. That's the point on the curve that we're looking at. And now let's write the equation of the tangent. And then once we've got that, we'll do the equation of the normal line. So the equation of the tangent line. Let's start with the slope. So the slope of a tangent is going to be f prime of 1. And so we already have our derivative, so let's just plug it in. So it's going to be e to the first, 1 times 3 over 2 times the square root of 1. So it's going to be 3e over 2. Okay, so that's the slope of the tangent line. And now for the actual equation of the tangent line, I'm going to use my point slope form to find that. So it's going to be y minus e using the point. Here's my point. Remember, you need two things for the equation of a line, a point and a slope. Got our point and our slope, so y minus e equals 3e over 2 times x minus 1. And remember, e is just a constant. So, I mean, we could approximate this, but I don't want to approximate it. I want the exact equation with the exact slope, and we can do that. Now let's just add e to both sides. So my equation of my tangent line is going to be y equals 3e over 2 times x. Now remember, that is the slope, right? I know it looks, it's not a variable, that is a constant, 3e over 2. And then we're adding, right, we're just adding e. And again, I want to have the exact, I don't want to approximate here. I don't want to go to my calculator. So I'm looking at this and I'm saying, oh, I just need a common denominator of 2. And so then it would become 2e over 2 minus 3e over 2. So that gives me a negative e over 2. And there is the equation of the tangent line at x equals 1. And now we did do, we did some, had to do some algebra and some arithmetic there, but there we go. Okay? Equation of the tangent line. Now, if I want the equation of the normal line, and let's just, because we ran into my second derivative down here, let's just bring it right here. So if I want the equation of the normal line, the point again, so let's just remember that our point was going through 1e. So the point, we're passing through the point 1e. So there's the point that we're looking at. And remember, the tangent line, the normal line is the line that is perpendicular to the tangent line. So we know what the tangent line is. We even know what the slope of the tangent line is. So if the slope of the tangent line is equal to 3e over 2, well, a line that is perpendicular, the slope of the normal line, is going to have to be the negative reciprocal of that. So it is negative 2 over 3e. Remember that it is perpendicular to the tangent line. Okay, perpendicular to the tangent line. So now we just do the algebra. So we've got a point and a slope, and our equation y minus e is equal to negative 2 over 3e times x minus 1. So y minus e equals negative 2 over 3e times x plus 2 over 3e. Let's add e to both sides. And y is equal to negative 2 over 3e. Now remember, that is the slope. And even though it looks kind of funky, right? But it's got that e in it. But I do want it exact. I'm not going to go in here and pull out a calculator. I'm going to just leave it exact. Need a common denominator to add these. So let's multiply by 3e on the top and the bottom here. And we end up getting 3e squared on the top plus 2 over 3e as the b value, my y-intercept in my slope-intercept form. Okay. Now we have a full view of of that problem that we've just done, which we took through both the first derivative and the second derivative, and then we did an application and asked where the equation of the tangent line and the normal line what those equations were at the specific point 1e at x equals 1. And so this was a really good example of, using our product rule and then taking it further and applying our knowledge about tangent lines and a new definition, or one maybe that you've heard, but a new definition for us in this video called the normal line, and looking at both the tangent and the normal line. So tried to get it all on the screen at one time. I know it's kind of small, but you can see the overview here of all that we did in that example.